Good morning everyone. So in today's session of high-speed aerodynamics, so we are going to look about the normal shock relation. So last session we have seen about what is shock wave and what is normal shock wave, right? So in today's session we will see what is the relation between the normal shock relations, how we are going to obtain. So first consideration in the case of normal shock, so what we will be seeing is that most of the places where we observe the shock wave is occurring is that at supersonic flow. So in which where we will be seeing this normal shock wave is frequently is at supersonic flow fields only we are going to observe. So what is normal shock wave? As we know, it is nothing but a normal shock wave which is perpendicular to the flow, right? So this one we will be calling it as a normal shock wave. So what do we know about this shock wave, normal shock wave? So what we will be having, density, pressure, temperature will be, and velocity and Mach number. So these properties ahead of the shock wave and behind the shock wave, how it is going to change. So now what we will be taking ahead of the shock wave, what we will be considering ρ1, P1, T1, V1 and M1. So these are the properties before the shock wave. So once it crosses the shock wave, once the flow field is crossing the shock wave, so once the flow field is crossing the shock wave, so what we will be happening? Our density which is there, it will be higher, pressure will be higher, temperature will be higher, but whereas velocity will be less and Mach number also will be less. So these two parameters behind the shock wave, it is going to change, right? So this is how the variations which we will be having. So we will be having ahead of the shock wave, so Mach number is above 1 and behind the shock wave, so we are telling M2 is less than M1, right? So that one specifically to tell M2 is less than 1, which means M2 is less than 1 means what? So it is nothing but behind the shock wave, we will be having the subsonic flow field we are going to observe, right? So ahead of the shock wave, we will be having the Mach number is higher, which means like velocity of the object is more than the speed of the sound. So because of that one, these particular compression waves forming the normal shock wave. So behind the shock wave, what will be happening is that the Mach number is going to be reduced. And in such a way that it will be falls under subsonic flow field condition, right? So the shock wave is a very thin region. So the shock thickness is usually in the order of free molecular free paths, typically 10 power minus 5 centimeter for air at standard condition. So the flow in the supersonic ahead of the wave and subsonic behind. So what we have seen in the previous diagram that, so we have M1 is greater than 1, M2 is less than 1, right? So further, the static pressure, temperature, density increase across the shock wave, whereas decreases for the velocity. So behind what we have seen, pressure, density and temperature is greater than the P2 ahead of the, whereas the velocity is less than the ahead of the shock wave when it is behind the shock wave, right? So nature establishes that shock waves in a supersonic flow is a solution to perplexing the problem having to do with the propagation of disturbance in the flow. So what nature will be established is that shock waves in supersonic flow. So we are telling that shock waves is forming at the supersonic flow, right? It is as a solution of perplexing problem having to do with propagation of disturbance in the flow. So means formation of the disturbance in the flow, right? So now what we will be going to see is that we will be comparing the subsonic and supersonic streamline flow over a flat faced cylinder or slab. So we are considering two sections. One where we are having the subsonic flow, second one where we are having the supersonic flow. So what is subsonic flow? What we know? That we have that Mach number which will be less than 1. So Mach number which is less than means what is the velocity of the object will be less than the speed of sound. So in case if you are writing the inferiority, it means what? Free stream, right? So means free stream velocity is less than the speed of the object. So this is for the subsonic flow. So whereas supersonic flow means what we will be having? Our free stream Mach number will be more than 1, which means that velocity of the object is more than speed of sound. So at this particular speed, what we are telling, we are having the formation of a shock wave, right? So that's what here we have seen, that there is a formation of the shock wave ahead of the object. That is nothing but flat faced cylinder we are seeing. So that is at supersonic flow, whereas at the subsonic flow we don't have the formation of the shock waves. So coming to the behind the shock wave, what we have seen already, that we will be having the Mach number will be less than 1 we will be observing. So to obtain some preliminary physical field for the creation of such shock waves, consider a flat face cylinder mounted in a flow. So what we have seen in the previous session, that example diagram, same diagram. The flow consists of individual molecules, some impact on the face of the cylinder. So whatever the flow which is passing, so individual molecules will be having on the face of this particular cylinder. There is in general a change in molecular energy and momentum due to impact with the cylinder, which is seen as an obstruction by the molecules. What we will be having generally in a molecule, in a flow, we will be having the molecules. So that particular individual molecules having some energy and momentum will be there. So those particular in a flow, what we will be having. So due to the cylinder presence, what will be there? That impact will be due to impact with the cylinder, which we will be seeing as an obstruction by the molecules. So therefore, just as in for our example of creation of sound wave, the random motion of molecules will communicate. Thus, there will be this change in energy and momentum in other regions of the flow. Because of this one, creation of the sound wave, the random motion of the molecules communicate this change. So whatever the molecules are present inside a flow, these will communicate with each other what the change is happened in the energy and momentum to the other regions of the flow. So the presence of the body tries to propagate everywhere, including the directly upstream by the sound. So whatever the body presence is there in a flow, this tries to propagate everywhere, including directly upstream of the flow by sound waves. So in figure, the incoming stream is subsonic, so which means velocity is less than speed of object. Speed of object is less than speed of sound. So the sound waves can work their way upstream and form on the flow about the presence of the body. So what happens is, like when we are having the velocity of the object is less than the speed of the sound, so these sound waves can work their way upstream and form on the flow about the presence of the body. So whatever the flow which is there, so it try to warn that there is a presence of the body is there. So the flow streamline begin to change the flow properties, begin to compensate for the body far away from the upstream. So when it gets to know that there is a presence of the body is there, or the one particular obstruction is there, so it try to change the flow streamline, and the flow properties begins to compensate for the body upstream. So in case second one which we are telling, so when we are having the velocity of the object is more than the speed of sound, so the sound waves can no longer propagate the upstream. So means the sound waves will not be able to propagate on the upstream. So instead what they do is, like they tend to collides a short distance ahead of the body. In doing so, the collides forms a thin shock waves. What happens is that, which we have seen in the figure B, that when there is a flow, we are seeing that there is a formation of shock wave, right? So what happens is, when we are having the velocity of the object is more than the speed of sound, the waves which are there, the sound waves, they no longer propagate the upstream. So what happens, this is because of that reason, the short distance ahead of the body, there is a formation of thin shock wave is going to present. So ahead of the shock wave, the flow will be no idea for the present. So what we have seen in the previous one is that when we are having the velocity less than a, the upstream flow will be having the idea of the presence of the body, and what they do, they tend to change their flow streamline and correspondingly there will be changes in the flow properties. But when there is a speed of object is more than the speed of sound, the sound waves will no longer propagate at the upstream, and those waves does not know that there is a presence of the body. So what we will be having? We will be having the shock wave presence. So immediately behind the normal shock wave, what we will be having? So the flow will be tends to be subsonic. Hence, the streamlines quickly compensate for the abstraction. So although what we have seen in the figure is the only in one many of the situation which nature creates the shock waves. The physical mechanism just discussed is quite general. So most of the explanation will be of the similar. So to begin with the quantitative analysis of changes across the normal shock wave, hence the normal shock wave assumed to be discontinuity across which the flow properties suddenly change. So what we are going to see is like we will begin to quantitative analysis of change across the normal shock wave. So across the normal shock wave, we are going to see what are the changes will be there with the help of quantitative analysis. Here, what we are going to do is like normal shock wave is assumed to be discontinuity across which the flow properties suddenly change. Okay. So first, assuming that all the conditions are known ahead of the shock wave. So this one, if we are taking it as a shock wave, this is region 1 and a region 2. So what we are doing is that one, at region 1 we are going to, we know what are the properties, all the conditions. So what we want to do is like behind the shock wave what is happening. So in this one what is condition, there is no heat added or taken away from the flow as it transfers the shock wave. Example, we are putting the shock is in a refrigerator, nor we are irradiating it with a laser. So what it means? Hence, the flow across the shock wave is adiabatic. No heat added or taken away from the system is what? It's nothing but adiabatic, right? Process. So, what we are considering is like first we are assuming that all the condition at the region 1 we know, and we are trying to find out what's happening across the shock wave. Means after the shock wave, what is happening? That is at region 2. So, and we are taking that no heat is added or the taken away from the flow. So, it means the flow is the shock wave is flow across the shock wave is adiabatic. We are considering. So now what we are going to see is that we are going to see the flow equation trying to solve, right? So what we know the continuity equation? Rho 1 U1 equal to rho 2 U2. So that is continuity equation we know. So what is momentum equation? P1 plus rho 1 U1 square equal to P2 plus rho 2 U2 square. So these are our conditions for what which we have seen in the last class, right? So one dimensional flow steady, right? So this is what, and we are telling that no heat is added at the adiabatic. So then what is the energy equation? H1 plus U1 square by 2 plus equal to H2 plus U2 square by 2. So this is the energy equation. So apart from this, what we require? We required the ideal gas equation P equal to rho RT and enthalpy equal to CPT. So what we are having? We have rho 1 P1, rho 2 U2, rho 2 P2, U2, T2 and H2. Why? Because we already know ahead of the shock wave region 1 rho 1 U1 P1 T1 H1. So we are taking all the condition at region 1 we know. So what we are trying to find out, what is at region 2, those terms we are have to find out. So basically what we have three equations, right? Continuity, momentum and energy equation. But how many unknowns are there? Rho 2, U2, 2, H2, 3. Then we are having the temperature change also we are having 4 and P1. 1, 2, 3, 4 and temperature 5. So 5 equation 5 unknowns are there. So we are having the apart from continuity, momentum and energy equation, we take the help of P equal to rho RT and H equal to CPT. So we have 5 equations and 5 unknowns. So then we will be able to find out the at region 2 what all the changes are going to happen for our flow properties, right? So now what we will be seeing is that we try to solve for the equation 1. So what we will be doing? We will be taking the equation 2 and divided by equation 1. So what is equation 2? P1 plus rho 1 U1 square equal to P2 plus rho 2. P1 plus U1 square by 2 plus P2 plus rho 2 U2 square by 2. So now what we are doing? We are dividing with the equation 1. So before that one, what we are writing is that P1 minus P2 equal to rho 2 into U2 square by 2 minus rho 1 into U1 square by 2. Right. So now what we are doing? We are dividing with the equation 1. So when we do with the equation 1, what we will be having? We have okay, this side and that side if you are taking rho 1 U1, then this will be rho 2 U2. So this will be rho 2 U2, this will be rho 1 U1. So that is what the condition, right? Like dividing with rho 1 U1, this with rho 2 U2. So once you are taking out those things aside, then what we will be having? Rho 2 cancel, U2 will cancel. Then these two will get cancelled, these two will be getting out cancelled. So what else we require for that one? We'll have to, sorry. So from here, this equation, what it is there? So this is nothing but P1 by rho 1 U1 minus P2 by rho 2 U2 equal to U2 minus U1. So what is A? We know. So A equal to under root of gamma P by rho. So now what it is there? P by rho, we can write it as A square by gamma equal to P by rho. Right. So now from here what we can write? P by rho is nothing but we can write it as A square by gamma. U1 will be there minus A2 square by gamma. U2 will be there equal to U2 minus U1. Right. So then what we will be having from this expression we will be having, we will be taking the equation 7 from this equation is a combination of continuity and momentum equation. Now what we will be taking is like the energy equation will be, what we will be doing, equation 3 can be utilized in one of the alternative forms of the energy equation. So what we already know, that one is A square by gamma minus 1 plus U square by 2 equal to gamma plus 1 by 2 gamma minus 1 into A star square. So this one we already know. So what we are going to do it here is that A1 square equal to gamma plus 1 by 2 A star square minus gamma 1 minus by 2 into A star square. So it means like from this expression we are getting the A1, then we are getting the A2. So now from this expression what we will be doing is like that is that, so A1 square equal to, this expression will be like that. So gamma minus 1, if we are going to the this side, if we are doing it means minus of U1 square by gamma minus 1 by 2. So if it is goes to the other direction, means other one means plus gamma plus 1 by 2 into A star square. So now this is alternative, we can write A1 square equal to gamma plus 1 by 2 into A star square minus gamma minus 1 by 2 into U1 square. So that is nothing but this is the expression, right? So similarly for A2 star square we will be find out from the same manner. Now since the flow is adiabatic flow, adiabatic across the shock wave, so A star in the equation and equation 8 and 9 will be having the same constant value we are going to obtain. Now substituting that equation 8 and 9 into 7. So what we will be getting is that, so what we will be having, seventh equation means. So this is right, A1 square by gamma U1 minus A2 square by gamma U2 equal to U2 minus 1. So we will have known what is A1 value, A2 value. So we will be finding out keeping those values, right? So A1, A2 values into that expression. So then what we will be getting, so what we know, A1 is nothing but gamma plus 1 by 2 A star square by gamma U1 minus gamma minus 1 by 2 gamma into u1 minus of gamma plus 1 by 2 a star square by 2 gamma u2 minus plus minus gamma 1 by 2 gamma u2 equal to u2 minus u1. So further, if you are going to solve for this particular expression, what we will be having that gamma plus 1 by 2 gamma u1 u2 into u2 minus u1. So what we are trying to do is like a star we are keeping it aside and u2 minus u1 we are keeping it aside. So that's where we will be getting this expression of a star square and u2 minus u1 separate, right? So this is the what we will be getting once we have taken that adiabatic across the shock wave, and which means like both equations will be having the a star value will be the constant value will be there, and we are substituting inside the equation 7, right? So now the pro expression we are dividing by the u2 minus u1. So then we will be having this particular one we will be getting. Now solving for the a star. Now for solving for the a star means what we will be having. So gamma plus 1 by 2 gamma u1 u2 a star square equal to 1 minus gamma minus 1 by 2 gamma. So we can write 2 gamma minus gamma plus 1 by 2 gamma. So what it is nothing but gamma plus 1 by 2 gamma. So gamma plus 1 get cancelled, 2 gamma get cancelled. Now what we can write here? So this is nothing but a star square equal to u1 u2, right? So now this expression is nothing but prime interrelation. So and it is useful for the intermediate relation of normal shock wave. Now for this further what we can write here? So 1 equal to u1 by a star we can write and u2 by a star we can write, right? So now further what this can be right now? 1 equal to m1 star and m2 star. So m2 star equal to 1 minus m1 star. So it means what it will be there? M2 will be less than m1 only, right? So the flow ahead of the shock wave must be supersonic, that is m1 is greater than 1. This implies m1 star is greater than 1. Thus from the above equation, that is m2 star equal to 1 by m1 star. So it means behind we will be having the less than. Hence the Mach number behind the normal shock wave is always subsonic condition only, right? This in general results not just limited to the calorific perfect calculus. So we will be recalling for the solving of the m star gives. So m square equal to 2 by this expression we already know. So from there we are finding out what is m star square equal to gamma plus 1 into m square divided by 2 plus gamma minus 1 into m square. So this is the equation we will be getting. Now we are substituting the equation 12 into the equation 1. So then we will be having the same expression only what will be in terms of for m star, in terms of m2 star and m1 we will be writing, m1 star we will be writing in terms of m1. So now over here we are trying to solve for the m2 square. So for that one we will be getting this expression 1 plus gamma minus 1 by 2 into m1 square divided by gamma m1 square minus of gamma minus 1 by 2 is the expression we will be getting. So now whatever the equation 14 above equation is there, it will demonstrate for the calorific gas value with constant value of gamma. So gamma value is constant. So the Mach number behind the shock wave is function of only Mach number ahead of the shock. So it means like behind the shock wave whatever is there, which is a function of ahead of the shock wave. So as you can see here, right, m2. So this is ahead of the shock wave. So m2 behind the shock wave is depending on the ahead of the shock wave. That's what here we are saying. So it allows that, it also shows that m1 equal to 1, then m2 equal to 1. So if you are taking m1 equal to 1 means what it will be? 1 plus gamma minus 1 by 2. Then gamma minus 1 by 2. So what we can write 2 plus gamma minus 1 by 2. Then 2 gamma minus gamma plus 1 by 2. So these do get cancelled out. So this will be gamma plus 1 divided by gamma plus 1. So this is nothing but m2 star square equal to 1. So when m equal to 1, so it also mn equal to m equal to 1. So this is a case for infinitely weak normal shock wave, which is defined as a Mach wave we will be defining. So if m1 increases above 1, the normal shock wave becomes stronger and m2 will be progressively less than 1. If it limits m1 tends to infinity approaches to a finite minimum value, which is the for the air is 0.378. So for that one, m2 will be approximate to gamma minus 1 by 2 gamma. Right. So the upstream of the Mach 1 is powerful matter which dictates the shock wave property. So M1 is the head of the shock wave, is the plays a major role to predict the flow properties, right, behind the shock. So ratios of the other properties across the shock wave also can also be found in terms of M1. So whatever we have, that pressure, density and velocity, pressure, density, velocity and temperature, we can find the different. So pressure is what we know, rho 1 u1 equal to rho 2 u2. So from here rho 1 equal to u1 by u2, right? So now further we can write it as u1 square by u2 and u1. So u2 and u1 is nothing but what? A star square, right? So this we can write it as m1 star square. So further what we can write? So what is m1 star square is nothing but gamma plus 1 by 2 into m1 square by 2 into gamma minus 1 into m1 square, right? So now to obtain the pressure ratios, we will be returning to the momentum equation, so that we know that P1 plus rho 1 u1 square equal to P2 plus rho 2 u2 square. So from here we can write, so P2 minus P1 equal to rho 1 u1 square minus rho 2 u2 square. So which combines with the equation 1 will be yielding that. So further what we are writing, so rho 1 u1 if we are taking out, so u1 minus will be having of P2 minus P1 equal to rho 1 u1 into u1 minus u2. So now from here we can write rho 1 u1 square equal to 1 minus u2 by u1. So now what we know, a1 square equal to under root of gamma p by rho, we will be knowing it, right? So now further one, so what we will be writing, p2 by p1 divided by p1 equal to gamma m1 square into 1 minus u2 by u. This we will be getting. Now further modifying of this one, u2 by u1 value, what we will be having, p2 by p1, p2 minus p1 by p1 equal to gamma into m1 square 1 minus 2 plus gamma minus 1 m1 square by gamma plus 1 into m1 square. Now if we simplify this particular expression, what we will be having, p2 by p1 minus 1 equal to gamma 1 into m1 square minus of gamma m1 square into 2 plus gamma minus 1 into m1 square divided by gamma plus 1 into m1 square, right? So further what we can write here, from this particular expression, or else further what we try to do is like we do this thing like when you have LCM we can take it out, gamma m1 square gamma plus 1 of m1 square minus 2 minus gamma minus 1 m1 square divided by gamma plus 1 into m1 square. So here m1 square will get cancelled out. So now further this expression we can write it as only this expression, right? So first let's write gamma, so gamma into gamma m1 square plus m1 square minus 2, right, minus 2 minus gamma m1 square plus m1 square. So what is like gamma plus gamma minus gamma will get cancelled out. So then we will be having 2m1 square minus 2 into gamma divided by gamma plus 1. So further we can write it as 2 gamma by gamma plus 1 into m2 square minus 1. So this one if we are taking out the left hand side means, right hand side means, so 1 plus 2 gamma by gamma plus 1 into m1 square, that is P2 by P1, right? So now to obtain the temperature ratio, we will be recalling the equation of state P equal to rho RT. So from there we know T2 by T1 equal to P2 by P1 into rho 1 by rho 2, right? So now we will be substituting the equation, what we will be having the pressure and density. So now what is H equal to CPT, right? So Cp will be, if it is cancelled out means what we will be having, H2 by H1 equal to T2 by T1. So that particular expression we will be writing 1 plus 2 gamma by gamma plus 1 into m1 square minus 1, which we have got. Then rho 2 by rho 1 expression is like this. So this is what we will be getting. So for a calorifical perfect gas with a given gamma value, we will be getting, they give the m2 and p2 by p1, rho 2 by rho 1, t2 by t1. So these all are the functions of m. So Mach number is a quantitative governance for the compressible flow. For such high temperature cases, we will be having a closed form of expression of equation from 14 through 22 are generally not possible, and normal shock wave properties will be calculated numerically. So beyond Mach 5 means the temperature behind the normal shock wave becomes high enough that gamma is constant, which does not exist. However, the flow regime m1 is less than 5 contains a large number of everyday practical problems. We will be seeing that m1 is less than 5. So the limiting case m1 is to infinity can be visualized as u1 is infinity, where the calorific perfect gas assumption is invalidated by the high temperature, as a1 equal to 0, where here the perfect gas equation of state is invalidated by the extremely low temperature condition. So when you are taking gamma equal to 1, so m2 equal to gamma minus 1 by 2 gamma. So that is nothing but 0.378, which we have already seen previously. So rho 2 by rho 1, when limit tends to m1 tends to infinity, then gamma plus 1 by gamma minus 1. So it means 1.4 plus 1 by 1.4 minus 1 equal to 6. So P2 by P1 it will be infinity and T2 by T1 it will be infinity. So it was stated that flow ahead of the shock wave must be supersonic. However, it is interesting to note that equation mathematically hold for m1 is less than 1 as well as m1 is greater than 1. So therefore, to prove that this equation has a physical meaning only when Mach number is less than 1. So we must appeal to the second law of thermodynamics, that is based on the entropy we have, right? So what is that one? We have the relation of S2 minus S1 equal to Cp into ln of T2 by T1 minus R into ln of P2 by T1. So now what we have, T2 by T1 values, P2 by P1 values we have. So we are trying to substitute those expression inside this one. So we have seen that T2 by T1 is nothing but what is T2 by T1 equal to H2 by H1 into P2 by P1 into rho 1 by rho 2, right? So that's what we are going to give. So this is the expression for that. So now this particular above expression demonstrates that entropy across the normal shock wave is only function of m1. So as you can see here, again we are having in terms of m1. So it means this is a function of m1. Moreover, if it shows that m1 equal to 1, so in case m1 equal to 1, what it will be having? 0. So here 1 it will be given. So here ln of 1 we will be having. So here ln of 1. So it is nothing but 0 only we will be getting S1 minus 2. So if m1 is less than 1, then we will be having S2 minus S1 is less than 1. If m1 is greater than 1, S2 minus S1 will be greater than 0. So therefore, since it is necessary that S2 minus S1 will be greater than or equal to 0, from the second law, the upstream of the Mach number must be greater than or equal to 0, right? So if M1 is subsonic, then equation above equation, what for entropy equation states that entropy decreases across the normal shape. So it is an impossible situation. So it means that we should have above 1 only for the Mach number, right? The only physical possible in the case M1 is greater than 1, which in turn dictates our equation. So that across a normal shock wave, the pressure, density and temperature increases, whereas the velocity will be decreasing and Mach number will be decreases to the subsonic wave. So what really causes that entropy increase across the shock wave? So the changes across the shock wave occurs over a short distance for the order of 10 power minus 5 centimeter. Hence, the velocity temperature gradients inside the shock structure itself will be very large. So, in the regions of these large gradients, the viscous effects of viscosity and thermal conduction will become more important. In turn, these are dissipative irreversible phenomena that generate the entropy. So, therefore, the net entropy increases predicted by the normal shock wave relation is conjunction with the second law of thermodynamics inappropriately provided by the nature in the form of friction and thermal conduction inside the shock wave structure itself. Okay. So when we are having the larger gradient, the viscosity effects of viscosity and thermal conduction are very important. In turn, what it leads is like we will be having the dissipative and irreversible phenomena which generates the entropy. So the net entropy will be increased by prediction of the normal shock relation in conjunction with the second law of thermodynamics, which provided by the nature in the form of friction and thermal conduction inside the shock. Right. So how do the total stagnation condition vary across the normal shock? Now we will be considering one figure that illustrates the definition of total condition before the shock wave and after the shock. So region 1, we already know ahead of the shock wave we will be having this temperature and pressure will be there and we have included the entropy. So considering this region, the imaginary state 1 where the fluid element has brought to rest asymptotically. So we are taking on a fluid element. So in that real state, we will be having the Mach number, pressure, temperature and entropy. So imaginary state where fluid element has brought to be rest in isentropically, we brought it to the rest. That's what will be happening. So when it is brought to the rest, we will be having the T0, entropy still S1, but temperature will be T0 condition. So real state, we will be having the M2, T2, S2. And in imaginary state again we will be resting it to the isentropically, then we will be having T0 to T02, whereas entropy will be same as S2 we will be having. So the pressure and temperature in state 1, the total values of T01 and T01 respectively. So whereas entropy will be S1 because the stagnation fluid element has been done by asymptotic. So in region 2, the element moving what we have seen P2, M2, P2, T2 and S2. So if we are plotting it to the respectively condition, what will happen? P0 to 1, T0 to we are considering. So S2 will be the same. The question is raised that how P0 to and T0 behind the shock wave compared to the P1 and T0 ahead of the shock. So to answer this question, again we have to consider the relation that you know H plus U1 square by 2. H1 H2 plus U2 square by 2 energy equation, right? So CpT1 plus U1 square by 2 equal to CpT2 plus U2 square by 2. So now the total temperature will be given by what will be CpT0. So Cpt plus U square by 2. So CpT01 equal to CpT02. So then T01 equal to T02. So total temperature is constant across the stationary normal shock. So now write an equation between the two imaginary state 1A and 2. So what we will be taking S2A minus S1A equal to Cp of ln by T2 by T1 in place of TA by 1A1 ln of P2A by P1. So S2A equal to S2 and S1A equal to S, T2A equal to T0 that is equal to T1 temperature. T2 equal to P02 and P1A equal to P0. So from this one, what we will be having here, T2A and T1A is 6. So it becomes L1. So what we will be having, S2A is S2 and S1A is S1. Right. So we can write this above equation as S2 minus S1 equal to 0 minus R ln of P2 is nothing but P02. P1A is nothing but P01. So now from here what we can write is that R into ln of P02 by P1 minus of S2 minus S1. So ln of P02 by P01 equal to minus of S2 minus S1 divided by R. Further we can write it as P02 by P01 equal to, this is the expression which we will be getting. So now the variations will be like this. So as you can see, the properties behind a normal shock wave as a function of upstream Mach number. So this is like entire Mach number. So the pressure P2 by P1 is increasing. So from here, this is the M2 value, how it is going to reduce. So this is the density value and this is the temperature value changing, and P0 by P1 value is going to change here like this, where we are considering the establishment. So the ratio of the total pressure across the shock wave depending on M1 only. So also because S2 is greater than S1 shows that P002 is less than P01. So the total pressure will be decreases across the shock. So here we are talking about the total pressure. Okay. So the curve shows that M1 becomes very large, T2 by T1 and P2 by P1 also become very large. So whereas rho 2 by rho 1 and M2 approaches to the final limits. So you can see rho 2 by rho 1 and temperature limits the final limits. P2 by P1 is going to increase with increasing in the Mach number. So P2 by P1 and T2 by T1 they are increasing, and rho 2 by rho 1 and M2 is leading to the its limits, right? So this is all about the normal shock relations which we have seen. So for this one we have referred the textbook of modern compressible flow with historical perspective by the J.D. Anderson for better understanding. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.